Hello class. So on this video, we're going to continue on section 6.2. Before I start, let me remind you of the corrections that I did in the previous videos that I mentioned in the message I sent yesterday. Right. So one was that I added the, let's see, where's theorem one? I added the domain restrictions, right, to theorem one, right, for S. Right. So domain restrictions to the function that you get after you take the Laplace transform. And then that was in section 1, 6.1, theorem 1. And then in section 6.2, we had in theorem 7, right? I'm sorry that I forgot to start relabeling the theorems again because I thought it was the same section, but sorry, not theorem 7, but in the slide before. So in section 6.2 on the slide called transforms of derivatives, the assumption should be that f is continuous. Right, and then work from there, right? But everything else is correct. Like the discussion is correct, right? Everything else is correct. Okay. So in the previous video, we went over this example, right? Now actually using different Laplace transforms to solve differential equations. And we saw that the method was pretty simple, right? You take the Laplace transform of both sides, right, of the ODE. You solve for y of s, big Y of s, right, which is the Laplace transform of y. And then you take the Laplace inverse of both sides. Right? So the process was very simple. In terms of us justifying taking the Laplace transform of a derivative, there were two ways that I mentioned it. The first way, and it's something that is done a lot in mathematics and especially in engineering, is that you take the Laplace transform first, right? Or you do all the work, you get a solution, and then based on the solution, right, you justify taking the derivative of the Laplace transform of the derivative, right? So what is it that you need to justify, right? So in this case, we want to take the Laplace transform of the y dt and of y. Right? So what do we need to justify? Well, to take the Laplace transform of the derivative, since it's the first derivative, we need f to be continuous and f prime to be piecewise continuous. Right? Based on this theorem, this is what we need to guarantee that the Laplace transform exists, and we have this formula. Right? And then here, of course, I gave you what the formula looks like for a couple of number of n. So n equals 1 corresponds to the first derivative, n equals to the second derivative, n equals to the third derivative, right? You can see the pattern, right? But those are the things we will need to justify. So for us to take the Laplace transform in this case, we would need to justify the y dt being piecewise continuous and y being continuous. Okay? So once we find the solution, we could look at y of t and say, okay, yeah, y of t is definitely piecewise continuous, and its derivative, it's again an exponential, so it's piecewise continuous, right? So that's one way, right? Do the work first and then justify it. The way that I prefer is using theorem 1 from section 2.4, right? So we have a theorem that guarantees us the existence and uniqueness of a solution to this initial value problem and gives us an interval that we can find explicitly, right? So in this case, since it's first order linear, we can use this theorem 1 in section 2.4, and we know that there exists a unique solution on the interval negative infinity to infinity. What is this? What does this mean? There exists a function, dy dt, a function y whose derivative exists on this interval and that satisfies the differential equation. Since the derivative exists, remember that the derivative existing is equivalent to the function being continuous. Right? So that guarantees y being continuous. And the fact that y prime is piecewise continuous, that's a little bit harder to justify. I can't think of an example in which in which y being continuous and the derivative existing would lead to the derivative not being piecewise continuous. So I tried to look it up. I tried to see if there was a counterexample for that. I couldn't find it. But for sure, for all of the problems that we do in class, if y, or let's say the nth minus 1 derivative is continuous, then that guarantees that the nth derivative is piecewise continuous. Right? So for us in this class, justifying taking the Laplace transform of this initial value problem, right, it's enough to either use theorem 1 in section 2.4 if it's first order linear, or use the theorem 1 in chapter 4, right, which is the generalization of this theorem, right, when we take higher order linear ODEs. So those were the two ways of justifying us doing this work, right? And then other than that, it was pretty straightforward. Now, so I want to do one more example of this, but before I talk about that, let me say something, because I mentioned that the Laplace transform is, first of all, in a sense, it's more general, right, than our other methods. Right? And the key reason for that is that it allows us to work with functions, specifically forcing functions, that are discontinuous. So we didn't see it in this example. And we won't see it in the next one, but we will see it in section 6.3 once we introduce step functions. We'll see how we can work with the Laplace transform to solve differential equations in which the forcing function, right, which in this case, the forcing function was just a exponential, right, e to the 4t, it's continuous, right? But what happens if the forcing function is discontinuous, right? And that happens a lot in applications, right? And I'll talk more about that in the next section, but in that sense, the Laplace transform is more general it's a more general method than the other methods we've seen. Right, so that's one thing I want to note. Let's solve, if possible, right, if the Laplace transform is defined, linear ODEs, non-homogeneous, in which g of t is only piecewise continuous, right? Not necessarily continuous. Or actually, let me use g of x, because we usually use x if there's no context. So that's one reason why the Laplace transform is very useful. And again, we'll see in the next sections how this occurs a lot in applications. The other thing I want to say is that the Laplace transform we're seeing is not the most general form of it. So the most general form of the Laplace transform is given by something similar, but not entirely the same. It would be given by the integral from 0 to infinity of e to the negative st times f of t dt. However, in general, s is a complex number. So s has the form alpha plus beta I. For our purposes, s is only a real number. And in most cases, s is just greater than 0 or greater than a. But in general, for the general Laplace transform, s is a complex number. So we would have to work with the complex plane, which we can't do in this class. That's why we only restrict s to being a real number. Now, in the case that s is just beta times I, right, so let me write something about that. So in the case that s equals beta times I, what we get is something called a Fourier transform. And we usually take it from negative infinity to infinity. So this would be negative beta I, f of t dt is called the Fourier transform of f, which again, you'll see in more advanced classes. Now, whether to use the Fourier transform or the Laplace transform has to do with the context of your system. Depending, for example, one might be more useful depending on the types of frequencies that you're working with. If you're modeling something that has to do with waves, right, or some sort of frequency happening, so think of sound waves. But I won't get too much into that. You'll see that if you see Fourier transforms in your most advanced classes. If you're taking engineering classes, you will for sure see them. Let's say when you take classes involving mechanical processes and stuff like that, you'll see stuff like this. So you'll go more in detail and you'll learn in which case would you use whatever transform. Do you use the Laplace transform or the Fourier transform? The last thing I want to say is that you can also define the Laplace transform as going from negative infinity to infinity. And again, there are reasons for which you would do this, but for our purposes, so we're only considering t greater than or equal to 0, we only have to consider the integral from 0 to infinity. But in systems where you would consider negative t values, right, then it would make sense to use this Laplace transform instead, right, where you take the interval to be from negative infinity to infinity. Okay. So there's some things that I wanted to say about the Laplace transform, things that we're not covering in this class, but that are important to know because you'll see them in other classes. Okay. Now, let's do one more example of solving an initial value problem. Right. So here we want to solve the initial value problem, y double prime plus 5y prime plus 4y equals 0, given the initial conditions that y of 0 equals 1 and y prime of 0 equals 0. First, let's use, since it's second order linear, we can use theorem 1 in chapter 4, right, to justify this, us using the Laplace transform on this equation, right? That is, we want to justify the conditions of this theorem, right? Because we want to take the Laplace transform of a derivative and we want to justify this somehow. Right? So again, using theorem 1 in chapter 4, right, what is this theorem? You basically have to label or you identify each of the coefficient functions. In this case, a2 of x is 1. Right? This is the function multiplying the second order derivative. a1 of x is 5. And then a0 of x is 4. And g of x is 0. Right? So what do you need for a unique solution for this initial value problem to exist and be unique? Right? And on what interval? Well, you need these functions to be continuous on whatever interval. You need a2 of x to not be equal to 0, right? And you need the interval to contain the input x equals 0 of the initial condition. Right? You can see that all of these conditions are satisfied easily. All of the functions are constants, which are continuous. Right? a2 of x is the constant 1, so it's never equal to 0. Right? So we can take the interval negative infinity to infinity, right? Or for our purposes, 0 to infinity, because we only consider t or x values greater than or equal to 0. But in general, it works over all real numbers. Right? Now, in this case, I'm just saying everything out loud, right? Because just for sake of time. But in the homework, make sure to write everything out. Right? Whenever I tell you to use a theorem, you need to make sure that all the assumptions are satisfied, and you write that they are satisfied and why. Okay. But in general, we know that a unique solution exists on negative infinity to infinity. Right? Since we know that a function y exists, and we know it's 2 times differentiable, again, by definition of the derivative, that implies that y prime and in term y are continuous. Okay, so that takes care of the first condition, that we need the up to the nth minus 1 derivative to be continuous. So in this case, f and f prime are continuous. And again, to justify that f double prime, or in this case y double prime, is continuous, I can't think of an example where y prime being continuous does not guarantee that y double prime is at least piecewise continuous, right, which is what we need. And again, for the purposes of this class, y prime being continuous, or more generally, the nth minus 1 derivative being continuous, is always going to guarantee for us that the second derivative is continuous. It is at least piecewise continuous, sorry. And again, in the general case, I can't think of an example where y prime or the nth minus 1 derivative being continuous does not imply the nth derivative being at least piecewise continuous. I really can't think of an example. If any of you want to try to find one or look one up and let me know, then please feel free to do so. But again, for this class, we always assume that the nth minus 1 derivative being continuous is going to imply that the nth derivative is at least piecewise continuous. So we satisfy all of the theorems and all of the conditions in theorem 7. So it's justified for us to take the Laplace transform of both sides. Okay, so that's the idea. Okay. So let me make a note of that. Okay, so this implies y and y prime are continuous on negative infinity to infinity, but for our purposes, we're only considering 0 to infinity. And in this class, and then possibly more generally, the nth minus 1 derivative being continuous will imply that the nth derivative is at least piecewise continuous. So either piecewise continuous or continuous, but at least piecewise continuous. Which then for us means that we know that y double prime is piecewise, at least piecewise continuous. On 0 to infinity, and the work is justified. The work of taking the Laplace transform is justified. Of using, let's say using. Okay. So all of this is just to justify us using the Laplace transform. Right? Now, you only have to write this if I ask you to justify. right? If I just ask you solve using the Laplace transform, then just go ahead and assume that everything works, right? But if I ask you justify using this theorem that the Laplace transform, that using the Laplace transform is justified, you would have to write out something like this, okay? If I tell you to justify it somehow. So now let's actually go ahead and, I don't know if I'll do all the problem, but at least I'll start you, and then you can finish it as an exercise. So we're going to take the Laplace transform of both sides. So I have y double prime plus 5y prime plus 4y equals the Laplace transform of 0. Let me see if I got that right. Okay, good. Okay, now the Laplace transform of 0 is 0. Just remember the formula. It's e to the negative st times 0, and then we integrate that. Well, but we're just integrating the 0 function, which is just 0. Okay, so we know this right-hand side is 0. Here we can use linearity. Separate it into each part. Move the constants outside. Oops, I should have moved the 4 outside and left it inside. I did it again. 4 Laplace transform of y. Okay. Now we go back to our formula for taking the Laplace transform of derivatives and write everything out. Okay. So our formula, so we're taking n equals 2, so we need s squared times f of s, right? In our case, big Y of s, right? Minus s, y of 0, minus y prime of 0. Okay, so plug that in. So we get s squared, big Y of s, because again, since we're using little y, we're going to use the same letter, but capital letter for the Laplace transform. Right? So minus s, y of 0, minus y prime of 0. That's just the Laplace transform of y double prime. Again, using this theorem here. Now, we need plus 5 times the Laplace transform of y. Again, use this theorem when n equals 1. Right, so we get s times big Y of s minus y of 0. Then plus 4 times the Laplace transform of y, which is y of s, equals 0. Now, what we're going to do is simplify everything, combine like terms, and see what we get. So, what do we get? For the Laplace transform, we have an s squared here, a 5s here, and a 4 here. So it looks like s squared plus 5s plus 4 times y of s. Okay. We have a minus s times y naught, y of 0. We're given that y of 0 is 1, right? So we have minus s times 1 minus y prime of 0, which we're given is 0. So minus 0. I'm just not going to write that. Then we have a minus 5 times y of 0, which is 1. Oops, sorry. I don't know why I changed colors. Right. Y of 0, which is 1. And I think that's it, right? I think I have all the terms. Now my s and my 5 look very similar, so let me try to make my 5 more like a 5, okay, something like that. Okay, so now solve for y of s, right? So first move everything that's not being multiplied by y of s to the other side. Right, so we add s plus 5 to both sides. And then finally, you divide everything. Now we're in the last step where we have to take the Laplace inverse transform. You're going to have to do linearity first, right? So separate this into sums, and then find the Laplace inverse of each part. So I won't do the whole thing. I'm just going to set it up for you. Right, so by linearity, we're going to have that, let me do it in black, that y of t is going to be equal to the Laplace inverse of big Y of s, which is going to be equal to, by linearity, the Laplace inverse of s over s squared plus 5s plus 4, plus, we can take the 5 out, the Laplace inverse of 1 over s squared plus 5s plus 4. And then you can finish as an exercise. You're going to have to do partial fractions, which we did in a previous example, so you should be able to do it. Okay. And that's it. That's the last example in this section. Now, notice that we aren't using the full power of the Laplace transform. Again, the reason why the Laplace transform is more powerful than the other methods is because of what I stated here. By the fact that the Laplace transform is going to allow us to find solutions to linear, non-homogeneous ODEs in which g of x is piecewise continuous, not necessarily continuous. We can't do that as of now with the other methods, right? So we're going to see how we can do this in the next section, section 6.3, where we're going to be talking about step functions. Okay, so that's going to be in the next video.